Hello everyone, in this video I will discuss the concept of derivatives. So previously we have developed the notion of limits, and now we're going to turn our attention to a graphical interpretation of the rate of change of a function. So this interpretation deals with the slope of a line tangent to the curve of a function. Before we jump on to derivatives, I'm going to talk about what is a secant line and what is a tangent line. A secant line is a line which intersects the curve at 2 points. So for example, this line intersects the curve at 2 points. So this is a secant line, and P and Q are the points of intersections of the line and the curve. What about the tangent line? A tangent line is a line which touches the curve only at one point. So for example, the red one is a tangent line. So if we ask ourselves that do we find the slope of a secant line? So from our knowledge of straight lines, we know that slope is difference in y coordinates over difference in x coordinates, or change in y over change in x. So we use 2 points. So use 2 points to find the slope. And it's easier in case of a secant line because we have already 2 points here on the secant line. But what if we want to find the slope of a tangent line? So in this case, we have only 1 point. So we only have 1 point. So what we can do here is we cannot find the slope using only 1 point, but maybe we can estimate the slope using the help of secant lines. So as we move our Q closer and closer to P, so we can have a better estimate of our slope of tangent, because then the slope of secant will become closer and closer to the slope of tangent. So let's say this is our another secant line, and Q is moved a little bit more closer to P, and this has Q dash. So that's our secant line 2. And similarly, we can move Q even more closer to P, and we can have something like this. And let's say the point of intersection here is Q double dash. So we see that as Q is moving closer and closer to P, so we can go even further. So the slope of secant line gonna approximate the slope of tangent line. So it means as Q is approaching to P, so the slope of secant is approaching to slope of tangent. So we can use the limit information to find the slope of tangent line. So use limit info. So we're going to use the information that what happens to slope of secant as Q approaches P. So as Q approaches P, then PQ is going to approach to the tangent line at P, and using this we can find the slope of tangent line. One thing that we need to notice about the slope of a tangent is, like, if you just have a straight line as your function, the slope of tangent at each point on this line is going to be same, because this line has constant slope. So straight line curves have constant slope. But if we talk about the slope of a curve which is not linear. So in that case, if you think about the tangent line at this point, the tangent line gonna have a different slope than the tangent line at this point. So you're gonna have multiple tangent lines at different points, and all those lines gonna have different slope. So basically, when we talk about the slope of a curve, it means we're gonna get a function that gonna tell us the slope of this curve. And for a specific point, we can just evaluate the value by plugging in those specific values of x. Before we jump on to the meaning of derivative and actual derivation of the derivative formula, I want to give an example of a physical context. So let's talk about the rates of change. And we'll talk in terms of velocity because we already know that velocity is equal to distance over time. And when we talk about the rates of change, we can talk about the average rate of change. So average rate of change versus we can talk about the instantaneous rate of change. Let's say we have this given function, which is y is equal to tan t square, and a particle is moving along this path. So on x-axis we have time, on y-axis we have distance in miles, and we want to figure out the average velocity or the average speed between 3 and 5 hours. So if you want to find the average velocity, that would be essentially the slope of your secant line PQ. Let's find average velocity between 3 hours and 5 hours. So average velocity would be change in distance over change in time. So change in distance over change in time. So distance would be, so in this case, the distance traveled is f3 when time is 3, and the distance traveled is f5 when the time is 5. So we got f5 minus f3 over 5 minus 3. Since ft is equal to tan t square, so it means wherever you have t, you're going to replace that by f5 would be 10 raised to the power 5 square, f3 will be 10 times 3 to square over 5 minus 3, which is 2. So we get 80 miles per hour. So this is the average velocity between 3 and 5 hours time. What about if we want to find the instantaneous velocity at when t is equal to 3 hours? So instantaneous velocity means velocity at any instant. So far, we do not have any sophisticated tools which we can use to find the velocity at any instant, at any instant time. So since we need 2 points, so I can approximate the instantaneous velocity by picking 3. So, and also I can pick a point that is really close to 3. So let's say I'm picking 3 and 3.01. So using these 2 points, I can approximate that velocity at 3 hours would be approximately, so just plug in the values in the function and we get about 60.1 miles per hour. So this is our estimate. This is not the exact value of velocity at t equal to 3 hours. So soon we will find the tools which will help us to find the exact value at any instant. Or in other words, the slope of the curve at any point. So let's revisit our discussion of instantaneous versus average. So the slope of secant gives us the average velocity. So if I have 2 points PQ on this second line, and let's say this is a point, so x value is x and corresponding y value is fx. Similarly, I'm taking another point which is to the right of x. So this point is x plus h and the corresponding y value would be f of x plus h. So if I have to write the slope of secant line, so that will give me the average velocity, or in other words, slope of secant. So that would be change in y. So change in y over change in x. We see that x and x cancel here, and we are left with f of x plus h minus fx over h. So this expression is called difference quotient, and it is our slope of secant. So this difference is h. So if we want to find the instantaneous velocity, so as we discussed earlier, so we can bring this q closer and closer to p. So limiting value of the slope of secant will give us the slope of tangent. So in this case, if I make h really, really small, so it means q is really, really closer to p. So in that case, we get the slope of tangent. So h must be approaching to 0. So for instantaneous velocity, we can take limit as h approaches to 0 of this difference quotient. Limit h approaches to 0, f of x plus h minus f of x over h. So this is our slope of tangent. This was our slope of secant. So we got the slope of tangent from our slope of secant by applying the limit h approaching to 0. And this is also called the derivative. So derivative is instantaneous rate of change of y, or change of y with respect to the x value. So now we can use this information to solve our previous question. So previously we were looking at what is the instantaneous velocity. So we were doing this example. So we were talking about finding the instantaneous velocity, and at that point we didn't know how to do it. And we just did a rough estimate by choosing another point closer to 3. But now we can calculate the same question again and see what is the exact instantaneous. So previously we had this function, and we're going to use this, and we're going to find the exact velocity at t equal to 3. Using the definition of instantaneous velocity, we get limit h approaches to 0, f of t plus h minus ft over h. And now we're going to plug in the values here. So limit h approaches to 0. So when we use tan t squared, so we're going to replace the input by t plus h. So wherever you have t in this function, you're going to write t plus h. So we got tan t plus h squared minus tan t squared over h. If we try to solve this limit, so first step is we try to put the value of h. So when we put the value of h 0 here, so we get tan t squared minus tan t squared 0 on the top, and also h is 0, so 0 on the bottom. So we got indeterminate form. It means we need to do some algebraic manipulation to solve this limit. So we're going to expand this, and then we're going to simplify it using the whole square formula. So a plus b whole square is equal to a square plus 2ab plus b square, we get t square plus 2ht plus h square minus 10t square over h. So in the next step, we're going to expand this. So we get 10t square plus 20ht plus 20h square minus 10t square. And if there are any like terms, combine them together. So in this case, we see that 10t square and negative 10c square, they cancel each other. And we are left with this expression. So now from here, we can see that. So on the top, we have 20 as a common factor, h as a common factor, and inside we are left with, okay, so I think I made a mistake here. So it should be 20h. It should be 10h square here. So this would have been again 10 here. And we cannot take 20 out, so it means we can only take 10 out. Or let's just take h out. So in this case, h, and then we have 20t plus 10h over h. So now we can see that h and h cancels, and we have limit h approaches to 0, 20t plus 10h. So now is a good time to put the limit. So when you put h equal to 0, so this term becomes 0. So we are left with 20t. So this is our instantaneous velocity for any value of t for the given function. But our goal is to find at t equal to 3 hours, what is the instantaneous velocity? So we can just plug in the value 3. So when t is 3, instantaneous velocity would be 60 miles per hour. So this is the exact velocity when time is 3 hours. So previously we found 60.1, which was our estimate. So it is pretty close. So thus, what we learned from all this discussion is, so nutshell is that the derivative is the instantaneous rate of change of y with respect to x. And we can write that in different forms. So we can write that as dy over dx, or we can use f prime x, or we can use y prime. So these all are the same thing. So these are just different notations. So basically, small change in y over small change in x. So that is your instantaneous rate of change of y with respect to x, and this is our derivative. So in the next video, I will discuss the delta method for finding the derivatives. So make sure you do watch that video as well. Thanks for watching.